Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see Rayleigh method. Okay. In previous video, we had seen the potential energy method, how to find with that one. So now, and unit load method also we had seen, right? So this is the next method by which we can find the deflection in the problem. So that's why this one is the Rayleigh method. Okay. So topic will be covered in this video is Rayleigh method. So first we will see the Rayleigh method because this method was found by the Rayleigh only, and later Rist combined with one particular condition that we will see. Okay, that becomes the Rayleigh method. So first let's start with the Rayleigh method. So according to Rayleigh, a beam vibrating in a normal or combination of normal modes has kinetic. So normal mode means there is no any force or anything, just whatever vibrating is there, just allow them to vibrate. So vibration in normal or combination of normal modes, right? Combination like instead of one beam, two, okay, but that should be in the normal mode, no damp, no force, okay, that type of mode has kinetic energy from its motion because it's now it's vibrating, so we'll have some motion. So because of that, what happened here? They will have some kinetic energy. So kinetic energy from its motion and strain energy from its displacement because it's vibrating like up and down. So now just see from here, if it start vibrating, like suppose this is the initial position, here it will start vibrating, right? So from here it displaced here, okay, and then again it come back here, again it goes. So whatever the displacement is there because of that energy, right? So from its initial unstrained state, so this is the initial unstrained state. Now from here it starts vibrating, so strained state. So whatever this displacement is there, and once it will go in this direction down, right? So this displacement, right? Because of the energy stored. Okay. So according to the principle of conservation of energy, the sum of kinetic and strain energy, right? Once they will have the motion, they will have, like suppose it started from here to here, right? So at this maximum, once it will reach, they have the maximum kinetic energy. But once it reached here, they have the velocity 0. Means what? That total kinetic energy converted to strain energy. And once it started, so here kinetic energy increases, right? And that, so the sum of total kinetic energy and plus strain energy will be there for up and down. One will be less, the other will be more. Where kinetic energy will be more, strain energy will be less. Where strain energy more, kinetic energy will be less. So the total sum should be, according to the conservation of law, that total sum should be the constant. So according to the principle of conservation of energy, the sum of kinetic and strain energy remain constant over the time. The sum, not individual one. One will increase, the other one will decrease. So their sum should be constant. In computing the beam's strain energy U, we assume that displacement are only due to bending strain. So displacement is because of bending only, not because of, like suppose we will apply the force. So what happened? Here some also that will go, that compression will be there. If we strain, that elongate, some elongation will be there. So that we are not considering, what we are considering only because of the displacement, right? So that assumptions we have to take. So this already we had seen, like U equals to m square integral of L m square by 2EI dz. So this is the strain energy. Now where what is m? Where m is minus EI d2V by dz square. So this is our m formula. So we can substitute that m here, right? So, but before that, what is this d2V by dz square? So this we have to find. Once we know this one, we can substitute here, and that we can substitute here. So let's see how to find the V. So because it's a vibration thing, right? So means what? Generally we are taking that vibration as sinusoidal curve. So that's why here that is there. So each element of the beam describes simple harmonic motion in the normal modes of vibration. So in normal mode of vibration, that harmonic motion, that is denoted by Vz, comma t. So V is the what? Velocity in z, comma t direction. So means once g, z also will vary, and with that time also, means with the position and time, velocity will vary. So what is the general equation? V of z. So that is the maximum magnitude with the position into sine omega t plus epsilon, right? So just here where Vz, that is this one, is, right? This one is the vibration amplitude at any section z where we are finding. Means this will be at the maximum position, then Vz will be the maximum. But here this is what? For that particular position where we are taking that z. substituting for V from above two equation we get here, right? Because this is there. So now what is there here? What we have, M equals to minus EI dV, sorry, d2V by dz square, right? So for V we are putting here, so equals to minus EI into d2. What is V? V is here, this one, that V of jet, Vz. So just simply writing V, okay, sine omega t plus epsilon by dz square. Meaning what? This we have to differentiate with respect to z. Okay, so d2V by dz square sine omega t plus alpha. Now this substitute in where? In the previous energy, that energy equation here, because now we have d2Vy, or you can just differentiate here and then you can substitute also. So let's see here. Okay, so let's substitute first to differentiate this one, then what we will get. Just see, m square di by dt is there, right? So first let's find the whatever the difference is there, because this v m square is required, means whole square of these things. Okay, so let's see after substituting what we will get. So firstly, what is m? M is integral of L m square by 2ei dz. So let's write here that m square, okay, this is for integral L m square by 2ei into dz, by 2ei into dz. So for m we have to put this one, means this whole square, right? So this is u equals to, so u equals to m square. So integral of this L m square is what? Minus ei d2 by dz square and into v sine omega t plus epsilon. Okay, this whole square. Okay, so now what we can say, whatever is there variable, that we will keep there, and we will, so this we know that this is Vz, right, that here we have taken. Okay, so now just see here what we can remove from here. Once we will take the square of that one divided by 2ei, right, divided by 2ei. So what we will get from here? Ei square, so this becomes two positive, so e square I square, right, then d2v by dz square into v square, right, into, so this will be whole square of this one into sine of square omega t plus epsilon, right. This from here to where? 0 to where. Now let's see what are the constant here, and divided by 2ei, right. So ei, 2 is there, ei, 1 ei cancel, right. Now what is constant here? 1 ei is left here, and this sine square omega t. So let's take out of the integration that one. Okay, so now taking ei sine squares and this 2, so 1 by 2, then ei sine square omega t plus epsilon, right, this is common. Okay, now what is left here? That d2v by dz square whole square into dz, this will be there, right. So just see here they just kept inside ei. I took ei also common, so now we got this equation, because ei is constant for that. If ei is variable with material, then we have to keep, or ei depends on what? That dimension of this one, then we have to keep ei inside, right, depending upon the given condition. So you can keep inside also, you can just keep this inside. When if it is constant, then simply you can take out of the integration. Okay, so now the kinetic energy K of a non-uniform beam. So this is what we got, that strain energy we got, right, use the strain energy. So now next, the kinetic energy K of a non-uniform beam. So just see here, this is for non-uniform beam with a distributed mass rho a z per unit length, rho a. So mass is what? Mass by volume, right, sorry, density by volume, right, or density is mass by volume, right. So from here mass will be what? Rho into v. What will be v? A into z. So rho A Z per unit length. So V is what? Area, rho area into length. This is M. But what we have to find? Mass per unit length. So M by L. Mass per unit length is rho A L by L. L cancel. So M by L, mass per unit length is rho A by L. Here A depends on what? Z. So that's why A of Z, because same like V of Z. So here A of Z. Z is not the parameter. It is variable with respect to Z. Okay, per unit length, and carrying concentrated masses M1, M2, M3 dot dot mm, means M1, M2, M3 so on up to mm, means any number of masses. Okay, at a distance of Z1, Z2, Z3 so on Zn, means like suppose if 3 masses is there, so M1 at Z1, M2 at Z2, M3 at Z3 so on Mn at Z1 from the origin can be written. So if that many masses are there, then how we can write? So Ke is what? Here half mb square. So m is rho into z and v square is here dv by dt z square into dz. So half mb square plus, this is mass per unit length, but because of mass at that point also is there. So this is what? Just here beam. So this is mass of the beam, right? So mass of the beam of kinetic energy. But now on that what we are doing, applying the load M1, M2, M3 so on. Means so just here, like this beam is there. This beam having mass, right? So their mass per unit length is what? Rho A, rho into Az. So this also will start vibrating, and what we are applying the load, that M1, M2, M3. So kinetic energy of this one plus kinetic energy of, because of this mass, will be the total kinetic energy. So for the beam we found, that is what? Here rho Az into del V by del T square. Okay. So now into dz. Now for all this one, so again for the same way it will be half mb square, right? So for that part, whatever the mass we are applying, so for first mass it will be half m1, right? Then del v by del t square. Okay. So next plus half m2, okay, then into del v by del z2 square, here z1 square, okay, plus so on, it will be half mn, okay, del v by del z, this will be, sorry, del zn square, like that. So instead of writing so many terms, again this we will write in the form of sigma. So what we will take, that mr. mr is for m1, m2, m3, m4 so on. So mr into v1. So just see here, del v by del t, right? Sorry, this is del t, okay, where at z equals to zr. So del v by del t at z1, del v by del t at z2, del v by del t at z3 so on, del v by del t zn, means whatever the number is there. So now put here a value of r. So when r is 1, right? So 1 to n means m1 del v by del t at z equals to z1 whole square. That will be kinetic energy because of first part, mass. Then put r equals to 2, that is for second mass. So r equals to 2 means m2 del v by del 2 at z equals to z2 whole square. So that will be the kinetic energy of second. So the total mass, whatever is there, if suppose 2 mass is there, then only you have to add 2 terms. If more than 2 mass is there or n number of masses is there, means you have to add n number of terms with that beam one. So now instead of writing so many like long this one, we are writing in short form as a summation. Means this shows sum of all. So here half will be common for all, right? Because that is constant. So that's why half taken out from the summation, that is common, and r equals to 1 to n mr, and after that del v by del t at that point where the mass is acting or mass is there. So at first position, that at z equals to z1, because here we assume for m1 that is at a distance z1, m2 at z2 distance from the origin. So at that distance. Okay. So now here what we have to do, we have to substitute here again that del V by del T value from the previous one, right? Like just we substituted. By substituting Vz from the strain equation into kinetic energy equation, we get, okay? So half omega square cos square omega t plus phi, because this value we have to put, right? First del V by del T into omega square. So differentiation of that one, and in this also del V by del T square we have to put. So here for this del V by del T, that is with respect to Z, this one, right? So here that cos omega t, that is this term, will be constant. Here t is not there. So just see here. This we can differentiate with two types. Let's see how. I am differentiating separately here with respect to t and with respect to z, and that we can see how to substitute. So first I am substituting this with respect to z. So v of z means here z is variable, other things are constant. So this is not z. So means sine omega t plus epsilon, that is constant, and Vz is dou v by dou z. Okay, dou v of z you can say dou v by dou z. So this will be with respect to z. Now same equation with respect to t. So v of t means now this time this Vz will be constant. Okay, and sine omega t will be this one. So let's differentiate this one. So Vz as constant. After that, integration of sine omega t as minus, right? Differentiating here, cos omega t plus epsilon, and differentiation of this will give you omega. So Vz, okay, this is plus Vz of what? Omega into Vz cos omega t plus epsilon. sorry. Omega of Vz cos omega t plus epsilon, right? So this is differentiate. Some with respect to t, this is with respect to Vz. Again you can differentiate because double differentiation is there, so this becomes omega square, okay, v of z cos of, that becomes sine omega t plus epsilon naught, right? So just like we have to substitute here, okay? So now after this one, del v by del t square. So del v by del t square, not del 2 v by del t square. Here we have to put del v by del t. So del v by del t is what? This one, right? Make it a square of this one. So del v, this is, or del v by del t. So del v by del t square is what? Omega v of z into cos of omega t plus epsilon square, whole square, right? So from this we can write here, this is del v by del t square equals to what? Omega square, right? V square of z into cos square omega t plus epsilon. Okay, so this will be del v by del t square. So substitute here del v by del t square here also. So from both the term that is there, so that we can take common. Okay, now what is left here? Vz square. So this is common because in this Vz is not there, so we cannot take v of z. So just v of zr square and mr. Here rho a of z and then v square dz. Right. So after taking this to common. Now, because K plus U, just it's given that strain energy and plus kinetic energy, sum of those two should be constant, right? So let's see, K plus U equals to constant, that constant is what? C, right? So from here, just sum of these two. So this one, right? So here, half sine square omega t plus epsilon into this one, integral of L ei d2b by dz square into dz plus. So this is what? This is U. Okay. From here to here it is what? Just me here. That is K. So this of U plus K equals to 0. Sorry, C. So U plus K equals to C. Right. So now what we have to do from here? So now let's see here. this is u and this is z. So in that case, now we will see the particular case what happened, because here just the omega t plus epsilon is there and omega t plus epsilon is there. It's sinusoidal, so that whatever the vibration will be there, like this one, right? So it depends on, at this point it will be different, at this point it will be maximum, then again it will start decreasing, then again it will goes for negative, then again after this it will be 0, positive, right? So how we will get that one? So just see here, right? So when omega t plus epsilon is 0, pi, 2 pi, means multiple of pi. So when 0, pi, 2 pi, so what is cos 0? Cos 0 is 1. Cos pi is minus 1, right? Similarly, cos 2 pi 0. Sorry, cos 2 pi 1, right? So like this, once we will substitute this one, cos 0. So just see here, when omega t plus epsilon has 0 we are putting. So this 0, right? So sine square 0, sine 0 is 0. So means this term is 0. So after multiplying, this whole term will be 0. So for omega t plus 0, pi, 2 pi, this term will be 0. Now here what we will get? Omega t plus pi as 0. So cos 0 is 1, right? So half omega square into this term. So for this all 0, pi, 2 pi, because cos 2 pi is also minus 1. So this term we will get that as minus. So plus, minus we will get for this term. So for 0, pi, 2 pi, this term will be 0. This term only we will have. Next, when it's a pi by 2, 3 pi by 2, then let's see here. Above equation is reduced to half omega square. Okay, integral of L rho a z v square dz plus r equals to 1 to n mr v of zr square equals to c. Means simply just see this term, right? So this term is there for 0, pi, 2 pi. Now next case, when omega t plus epsilon is what? Pi by 2, 3 pi by 2, 5 pi by 2, right? Then what happens? So just see here again in this equation. So pi by 2, sine pi by 2, sine pi by 2 is what? 1, right? And cos pi by 2 is 0. So put that omega t plus pi, so sine 0, this becomes 1. So half into this term, right? This cos pi by 2 as 0. So 0, so cos 0 is, sorry, cos pi by 2 is 0. So 0 into omega square 0, 0 into this term. So this term, this whole term will be what? 0, right? For pi by 2, 3 pi by 2. And this time this will be there. So let's see here, for 0, pi, 2 pi, 4 pi, this term will be 0, this term will be there, right? 4 pi by 2, 3 pi by 2, this term will be 0, this will be there. So now what we will get after putting as sine pi by 2, half, this becomes 1, half integral of L ei d2 v by dz square into dz. So here half integral of ei d2 v by dz square, okay, by dz, that equals to c, right? So this is when pi by 2, 3 pi by 2, that is there, omega t plus epsilon value, where epsilon is the phase difference. Remember, this is the phase difference. In other words, the kinetic energy in the mean position equal to the strain energy in the maximum displacement position, right? Kinetic energy in the mean position is equals to a strain energy in the maximum displacement position. So wherever it maximum displacement is there, so see, just now I showed, right? So here this is the mean position, and just here kinetic energy in the mean position equals to a strain energy. So this is the kinetic energy at mean position, and that will be the maximum displacement, right? So that will be the maximum displacement position, right? So that is here only. So at this point, that kinetic energy is the mean at mean position, because here kinetic energy will be lesser. Here also it will start decreasing. So means from here it starts increasing. Here it will be maximum, then here it will be decreasing. So at this point, the kinetic energy will be maximum, and that is the maximum displacement position. Okay. So now from here, what we will do? We have to find the omega square. So from which equation you can find omega square here? Why? Because now this we have the c, right? This is equals to c. So put this one here. So what we will get? Half omega square, this term equals to this term. Okay, then integral of L rho A z V square dz plus sigma r equals to 1 to n mr v of zr square equals to, for c we will write this value, half integral of L E I d2 by dz square whole square dz, right, this one. So now half cancel, so what we have to find? Omega square. So just this whole term will be divided here. Okay, so just here, this divided by this term you can see here, half EI d2 by dz square whole square dz, half integral of L, so half already cancelled here, so integral of L, integral over L EI d2 by dz square whole square dz, so this one, and then this whole divided, so you just see here, integral of L rho A z V square dz plus sigma r equals to 1 to n mr v of zr whole square, so this term. So this is the omega square. So what will be the omega? A square root of this whole thing. So that omega will give you the natural frequency. So just see here. Okay. If Vz is known, above equation gives the exact value of natural frequency for a specific mode. Means what? Here only that Vz is required. Mass will be there, and that what is a mass? This also. So if Vz is known, we can find the exact, right, natural frequency. So that is it. If Vz is known, above equation gives the exact value of natural frequency for a specific mode. Rayleigh's principle states that if a mode is assumed that satisfy, let's see here, if a mode is assumed that satisfy at least the slope and displacement condition at the ends of the beam. So at the ends of the beam, whatever the slope is there and the displacement is there, if that's satisfied, then a good approximation to the true natural frequency will be obtained. Means at slope and displacement at the both end of the beam will satisfy, then we will get the approximate good result or good natural frequency, or you can say the true natural frequency we can obtain. As previously stated, if the assumed normal mode differs only slightly from the actual mode, but we assume that as normal mode, not the actual mode, because earlier in the starting itself that as we assume that it should be in the normal mode. The stationary property of the normal mode ensures that the approximate natural frequency differs only slightly from the true value. So if that normal mode is slightly different from the actual one, so then what happened? The natural frequency also will be slightly different. Furthermore, the approximate frequency will be higher than the actual frequency, right? Because of that, natural frequency will be there, but what happened? Approximate frequency will be higher than the actual frequency, because the assumptions of approximate mode implies the presence of some constraint that force the beam to vibrate in a specific manner. So once its approximate mode is there, that means what? In some certain condition like sinusoidal curve, that will be there. So because of that, what happened? Approximate frequency will be higher than the actual one, which increases the frequency. Okay. So now after this was the Rayleigh method. Now in this, what happened? Rayleigh-Ritz method. Okay. So just see here how Ritz modified that one by combining Rayleigh's and Ritz. Okay. So by assuming a finite series for Vz, finite series. So that was 1 to n, not finite. That was not finite, right? So Rayleigh for only Rayleigh is for infinite, but Ritz combined, that becomes for the finite series, because from the infinite series only they just put some constraint up to what that become given by that idea given by Ritz. So Rayleigh-Ritz method. So just here, by assuming a finite series of Vz, the Rayleigh-Ritz method extends and improves the Rayleigh method's accuracy. Now instead of finding 100, if you will find 4 or 5, what happened? You will get more exact value. So Rayleigh given for the infinite series, just like indefinite integral. We cannot find there what we are putting after integral. We are putting one constant c, because that we know that is not the exact value. But once it becomes the what? Definite integral, then we are getting the exact value. So same here. So indefinite integral type is Rayleigh method and definite integral type is Rayleigh-Ritz method. So for the even Rayleigh-Ritz is more accurate than the Rayleigh method. Okay. So now Vz is what? S equals to 1 to n. Just here they assume that S, like they are equals to, so here S equals to 1, B S Vs of Z means B1 of Z, B2 of Z. So now what is there? Where each assumed function V of Sz satisfies the slope and displacement condition at the B means the parameter Bs are arbitrary. So this Bs are just arbitrary, that any arbitrary constant is there, right, for that particular point. So when V1Z is there, that time whatever the arbitrary parameter is there, that is V1. When V2 of Z is there, then that arbitrary parameter is V2. The natural frequencies are then approximated by substituting V of Z in the natural frequency equation. So now V of Z approximated there, right? Substituting Vz in the omega square value, that what we got here. Okay. The parameter Bs are chosen to minimize these frequencies, reducing the effect of implied constraints. So whatever the implied constraint is there, that Bs should be such that they minimize the frequencies that we have to choose. Bs such as are reducing the effect of implied constraint. Bs, that parameter should be such that they can reduce the constraint in that. After selecting a suitable series, the method of solution is to create a set of equation. Right. Now just put that one. So del omega square by del Bs, because that parameter differentiate with that parameter. So first means what? Just find this one. Now with respect to that parameter, because in terms of that parameter only, and that parameter we assume we have chosen, so means that we have to remove that parameter. So what we will do? Just differentiate with that parameter, right? So yeah, after finding omega square, del omega square by dl means that del Vs equals to 0, where S is what? 1, 2, 3, and so already here S equals to 1, 2, n. So del omega square by del B1, del omega square B by del 2, del omega square by del B3, so on, that should be equals to 0, right? So once this will be 0, means that parameter got removed because we differentiated with that parameter. So wherever that parameter will be there, that becomes 1. By removing the parameter Bs, we get an nth order determinants in omega square whose roots give approximate value for the beam. Okay, for the beam's first and natural frequency. So for that particular natural frequency of that beam of n natural frequency, what happened? That this will give nth order determinant in omega square whose roots gives approximate value. So nth order is there, means definitely n value will be there of that omega. So first and natural frequency we will get from that beam. Okay, so this is the Rayleigh method. Okay, so in this, if you have any doubt, you can just contact me or you can just comment on the video. Okay, I will clarify your doubt, but I will just reply in the comments. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.